Everyone, myself Dr. Ravichandra Janapati, Associate Professor of EC Department. In this lecture, I am going to discuss regarding signal science system subject. In this, I am going to discuss regarding fundamentals of signal science systems as well as classification of signals. First, I will start with definition of signal. After that, definition of system and few examples. After that, we will discuss classification of signals. First, I will start with definition of signal. What is meant by signal? What are the examples of signals that I will discuss first. Then second, system with examples. Then classification of signals. These are the topics I'm going to discuss in this lecture. Next, first I will start with definition of signal. Here, signal is a function of one or more variables that conveys information on the nature of physical phenomena. It is a function of one or more independent variable. Signal is a function of one or more independent variable. It is a one or more independent variables that convey information on the nature of physical phenomena. So signal can be defined as it is a physical quantity which gives some information. That is to be known as signal. Now coming to the examples of signals, we have different examples. In that, one is voltage signal, which gives the information related to voltage. Another example is current signal, which gives the information regarding current. Heartbeat signal, which can be measured by using electrocardiogram. Another signal is blood pressure signal, which gives the BP of a particular person. So temperature signal, which can be measured from the environment using thermometers. Another one is brain signals that are EEG, which are measured by using EEG, electroencephalogram. So what is all these signals? All these signals conveys some information. How they are conveying? Which depends on some independent variable, which is a function. Mathematically, we can represent these signals as a function of one or more independent variables. Let us take voltage signal. Here, let us take voltage signal. There are independent variable in this voltage signal. That is, time is the independent variable. T is. Let us take the time on x-axis and amplitude, voltage of the amplitude. Here V on x-axis, y-axis. Sorry. Here I am going to take V on y-axis. which gives the amplitude of the voltage with respect to the time, where time is a independent variable. Here V is a dependent variable. Here, if I am going to take this voltage, here it will be like this. This is called as a voltage. In a similar manner, if I am going to measure the current, which depends on time, okay, now that is called as a time signal. If I am going to measure current, that is I, that is called as a current signal. In a similar way, heartbeat, ECG signal, heartbeat of a particular person with respect to time, blood pressure of a particular person with respect to time, temperature of the environment with respect to time, brain's measurement of brain signals from different locations of the brain, which gives EEG with respect to time. All these signals conveys some particular information. So these are the different signals. Now, coming to one-dimensional signal, multi-dimensional signal. Based on the independent variables, number of independent variables, we can define the signals into one-dimensional signal, that is simply called as 1D signal, and multi-dimensional signal. That means more than one independent variable. That means two-dimensional, that is 2D signal, three-dimensional 3D signals. So nowadays we are going to watch movies in 3 dimensions. Now coming to the examples of these 1D signals, each is the best example for one-dimensional signal. Here, which depends only on one independent variable, on a single variable. So speech is the best example for 1D signal. Let us coming to the multi-dimensional signal. Multi-dimensional means more than one independent variable. The function depends on two or more variables. Let us take image or picture, example of multi-dimensional or two-dimensional signal. Next, 3D video. Nowadays, most of the movies are making in 3-dimensional. So, where we have three independent variables. This is called as a 3-dimensional signal. Now, let us here. Now, we will define system. Here, we are going to define system. What do you mean by system? System is an entity, a connection of components which takes an input signal, performs some operation on it, and gives the response or output. That is called as a system. System is an entity, a collection of elements which takes input signal. Let us take x of t is the input signal, x of t. Usually, conventionally, we will take x of t as the input signal. X of t is the input signal. Then y of t is the output signal. This output is also known as response of the system or output signal. That is denoted by y of t. Now, this is the input, this is the output. In between, the system perform some operations. It performs some operations. So that is the main job of the system. Hence, the system is an entity or collection of elements which takes an input signal, performs some operation on it, and gives the response or output signal. Mathematically, this can be represented as y of t is equals to y of t is equals to transform on x of t. Y of t is equals to transform on x of t, where y of t is the output, x of t is the where y of t is the output, x of t is the input. This transform is the operation on that particular input signal. So this is regarding system definition. Now let us coming to the examples of systems. Let us coming to the examples of system. Nowadays, all communication systems comes under example of systems, like mobile phone, TV, radio, all are comes under this system. Examples of system: mobile, TV, radio, etc. All are comes under communication systems. A similar way, automatic speaker recognition system. This is also one of the application of AI, as well as it also comes under our speech processing speaker recognition system. Another one is aircraft landing system. So there we have navigation, we use GPS, we are going to use different devices which takes input signals and which use to track the aircrafts. That is also another example. Not only these communication systems, we have mechanical systems, electrical systems, some computer systems, etc. Engineering device discovery comes under system. If you take any gadgets, any device which takes input signal, performs some operations on it, and gives the response, that is called as a system. Now, coming to classification of signals. Next topic is classification of signals. Here, signals based on their characteristics that can be classified into different categories. In that, we are going to discuss only few categories. In that, the first one is continuous time and discrete time signals, periodic and non-periodic signals, causal and non-causal signals, deterministic and non-deterministic signals, even and odd signals. These are the different categories of the signals. Signals can be classified into different types. On what? Based on their characteristics. So if we take one category, means it is a continuous and discrete. Another category is whether it is a periodic or non-periodic. This non-periodic is also called as aperiodic signals. Causal and non-causal signals based on the existence of the signals. Deterministic and random signals based on the representation of the signals. Another one is even and odd signals. Not only these, but here these are the important classification. We are going to discuss about these classification. This is regarding the classification of signals. Now, in the first category is continuous time and discrete time signals. Continuous time signals can be defined as the signals that can be defined at every instant of time. That signals are known as continuous time signals. The signals that are defined at every instant of time, the signals are known as continuous time signals, which are these continuous time signals, which are denoted by x of t. These continuous time signals are denoted by x of t. The signals that are defined at every instant of time, and the signals that are continuous in nature. The signals that are continuous in nature, the signals are known as continuous time signals. Now, another classification is discrete time signals. Discrete time signals. Now, discrete time signals, here the signals that are continuous in amplitude, but discretized in time interval. Continuous in amplitude and discretized in time interval. The signals are known as discrete time signals. The signals that are continuous in amplitude. The signals that are continuous in amplitude, but discretized in time interval. Let us check. Here, these are continuous in amplitude, but these signals are discretized in amplitude. These signals are called as discrete time signals. Continuous time signals that are denoted by x of t. Here, look at here. Here, the continuous time signals are denoted by x of t. Discrete time signals that are denoted by x of n. Discrete time signals that are denoted by x of n. Discrete time signals are denoted by x of n. These are the best examples of continuous time and discrete time signals. Here, let us take continuous time signal. The first example, this is the continuous time signal. Now, this is continuous in amplitude. This is continuous in amplitude as well as continuous in time interval. Continuous in amplitude as well as amplitude. This signal is the best example for continuous time signal. Here, in a similar way, discrete time signals. This is the example of discrete time signal. Here, this is also continuous in amplitude. The signal that can be here, amplitude is same. Here, the amplitude is similar, but here it is discretized in time interval that is not defined at every instant of time. This is discretized in time interval. In the x-axis, it is discretized. So the signal is not defined at every instant of time. The signal that is not defined at every instant of time. Hence, it is called as a discrete time signal. Here, the continuous time signals, here, these are denoted by x of t. Discrete time signals, these are denoted by x of n. Discrete time signals are denoted by x of Now, next category is periodic and non-periodic signal. This periodic as well as non-periodic. This non-periodic is also known as periodic signal. This periodic and non-periodic. This non-periodic is also known as periodic signal. Now, first we will define what we mean by periodic signal. Periodic signals have the property that x of t plus or minus t is equals to x of t. X of t plus or minus t is equals to x of t. So here we have the property of x of t plus t is equals to x of t. This signal is known as periodic signal. Similarly, or x of t minus t is equals to x of t. Similarly, x of t minus t is equals to x of t. This signal is also known as periodic signal. So what do you mean by periodic signal? Here theoretically, the signal, if it repeats after certain interval of time, if it repeats after certain intervals of time, that signal is known as periodic signal. The signal, if it repeats certain interval of time, that signal is known as periodic signal. Let us take this particular signal. Here this is x of t. This is one particular signal x of t. The shape of the signal is here, it will be like this. In the x-axis t, y-axis is x of t. The shape of the signal will be like this. The shape of the signal is like this. Now, the same signal, here it is repeating after some particular interval of time. After some particular interval of time, the same signal is repeating. Hence, it is called as periodic signal. Hence, it is called as periodic signal. So the same signal it is repeating. The same signal it is repeating. Hence, it is called as a periodic signal. Now, another example is causal and non-causal signals. Causal and non-causal signal. Here, the causal signal can be defined as a signal is zero. Signal is zero for signal is zero for t less than 0, and non-causal signal is known as a signal is 0 for t greater than 0. So causal means x of t is equals to 0 for t less than 0. This signal is known as causal signal. This signal is known as causal signal. In the similar way, according to the definition, x of t is equals to 0 for t greater than 0. This signal is known as non-causal signal. Now, the examples of causal and non-causal. Let us take this. There are two signals are there. We have two signals. This is 1. This is 2. This is signal 2. Here, this is another signal. Now, here, this is second signal. This is second signal. Now, just observe the first signal. Observe the first signal. Here, x of t, it is exist only for positive side of the t. X of t is exist only for positive side of the t. It is not exist for negative side of the t. It is not exist for the negative side of the t. Hence, it is a causal signal. The first signal is a causal signal. This is the example of causal signal. This is the example of causal signal. Now, let us observe the second signal. Here, x of t is 0 for t greater than 0. For t greater than 0, x of t is 0. Hence, it is a non-causal signal. Just observe for t greater than 0, it is 0. For t less than 0 only, signal, the second signal is exist. Hence, it is called non-causal signal. It is the example of non-causal signal. In a similar way, right-handed as well as left-handed signal. A right-handed signal is 0 for t less than t. This is right-handed signal. The signal only exists right side of the t. Hence, it is called as right-sided signal. As well as left-handed signal means the signal exists only for negative side of the t. Negative side of the t. Hence, it is called as left-sided signals. It is called as left-sided signals. Now, deterministic and random signal. Next, another classification is deterministic and random signals. Deterministic and random signals. So, deterministic means here the behavior of these signals is predictable with respect to time. The signal that can be measured or predicted, that signal is known as deterministic signal, or the signal that can be represented with any mathematical expression. The signal, it can be predictable with respect to time, or it can be measured, or it can be right in any mathematical form. That signal is known as deterministic signal. The signals are known as deterministic signal. And in deterministic signals, there is no uncertainty. In deterministic signal, there is no uncertainty with respect to its value at any time. There is no uncertainty. There is no uncertainty with respect to time in deterministic signal. These signals can be expressed mathematically. These signals can be expressed mathematically. These signals can be expressed with mathematically. Y of t is equals to x of t plus x of t plus 3. In the similar way, here we can represent these signals in any mathematical form. For example, x of t is equals to sine of 3t. This is a deterministic signal. This signal can be determined. The value of this particular signal here, it can be defined at any instant of time. So hence it is called as a deterministic signal. Now another signal is random signals. Random signal means it is not predictable with respect to time. Random signals means these are not predictable with respect to time. Here, the behavior of these signals is random. The behavior of these signals are random. The behavior of these signals are random, and these are not predictable with respect to time. These are not predictable with respect to time. There is an uncertainty with respect to its value at any time. These signals can't be expressed mathematically. These signals can't be expressed mathematically. For example, thermal noise. The example of a random signals, the best example is thermal noise. Here, let us take, we have one signal here. In the x-axis, we have something T. In the y-axis, we have some another variable. Here, if the signal will be like this, here, thermal noise or something. Here, this is the example of random signal. The best example is noise. Noise means it is an uncertain signal. We cannot predict that particular signal, or we cannot express that signal in mathematical form. That signal is called as random signal. That signal is called as random signal. Now, even and odd signal. Next, another category is, another classification is even and odd signal. Even signals means it is a symmetric signal. Even signal means symmetric signal. The signals which are symmetric about the origin. The signals which are symmetric about the origin, that signals are known as even signals. And odd signals. The signals which are asymmetric about the origin, the signals are known as odd signals. The even signals are represented by xe of t. Even signals are represented by xe of t. Here x suffix. Next, odd signals are represented by xo of t. Odd signals are represented by xo of t. Mathematically, the even signals can be represented as xe of t is equals to xe of minus t. So the positive side of the signal is equals to negative side of the signal. If I am going to keep, if plus t, instead of plus t, if I put minus t, the signal should be same. The signal should be same, symmetric about the origin. That signals are known as even signals. xe of t is equal to xe of minus t. Next, another category is odd signals. Odd signals means xo of t is equals to minus of xo of minus t. xo of t is equals to minus of xo of t. Now, here, this is, for example, let us take this is x of t. Now, this is c of t, this is x odd of t. So, what is this x of t? What is this x of t means? Here, normally, most of the signal are purely even signal or not purely odd signal. Each signal consists of either some even component as well as odd component. Even component as well as odd component. Now, here, each signal, it consists of even component as well as odd component. Hence, here x of t is equals to find out the even component, the formula will be xe of t is equals to 1 by 2 or 0.5 into x of t plus x of minus t. You get my point? Here, in a similar way, here, to find odd component of the signal, we can use x odd of t is equals to 1 by 2 x of t minus x of minus t, or 1 by 2 x of t minus of x of minus t. Let us take this is a x of t is given. Now, here to find the even component, odd component, we can right like this. Now, this is regarding even and odd component signals. We can define some more examples also. This is the formula for even and odd. Even means x of minus t is equal to x of t. This is for continuous time signals, as well as for discrete time signals, x of minus n is equal to x of n. In the similar way, odd signals, x of minus t is equals to minus of x of t. X of minus n is equals to minus of x of n. Now, the signal can be expressed as combination of even part as well as odd part. The signal can be expressed as combination of even or summation of even and odd part. X of t plus x of t. In the similar way, x of minus t is equal to, why? Because x of minus t is equal to minus t, but x of odd of minus t is equal to minus of x odd of t. So hence, now we can find out c of t. Even component of the signal is equal to 1 by 2 x of t plus x of minus t. Odd component of the signal is equal to 1 by 2 x of t minus of x of minus t. This is regarding even and odd signals. Now, next, another classification of signals are bounded and unbounded signals. Bounded as well as unbounded signals. So now, bounded means here, bounded means finite. Unbounded means infinite. For a bounded input, if it produces bounded output, that is called as a stable signal. That is called as a stable signal. If the signal is bounded, that means if I am going to increase the time, now here the signal value is reaches to some, let us check here. Here we'll check what is bounded signal, what is bounded. Bounded means we have to remember that is finite. Unbounded means infinite. Bounded means finite. Let us take this signal. This is the bounded signal. Now, here this bounded signal, which is reaching zero value. Here the time is increasing, it reaches infinite zero value. That is bounded signal. Now the time is increasing, the signal is reaching infinite value. So this is unbounded, this is bounded signal. This is bounded signal. Now, in a similar way, here, now, next classification is energy and power signals. Energy and power signals. The energy of a signal that can be defined as E is equals to integration from minus infinity to plus infinity x square of t dt. That is defined as energy signal. As well as power signal. Power signal, it can be defined as mathematically limit of t tends to infinity 1 by 2t integration from minus t to plus t x square of t dt. This signal is known as power signal. Now, energy means E is equals to integration from minus infinity to plus infinity x square of t dt. That is known as energy signal. Power means P is equals to limit of T tends to infinity 1 by 2 T integration from minus T to plus T x square of T dt. This is known as power signals. Now, here there is a differences between power signal and energy signal. These power signals are infinite duration signals. Infinite duration are some periodic signals almost. Now, energy signals are finite duration signals. These are normalized power is finite and non-zero. Normalized energy is finite and non-zero. For power signals, normal energy is averaged over infinite time and it is infinite. Power signal, energy is infinite. For energy signals, the power should be equal to, average power should be equal to 0. Here, power signals are mathematically trackable signals. Here, energy signals are physically realizable signals. So these are the energy and power signals. From this, here we are going to complete classification of signals. Now, in this lecture, we have defined what we mean by signal. Here, we have defined what is meant by definition of the signal. Then after that, classification of signals. These are the topics we have discussed in this particular lecture. Thank you, one and all.